Okay, here's my graph for e to the h minus 1 over h. All right. Yep, graph there. Okay. All right. I zoomed in a little bit. And this is 1 right here. So we know the graph has a hole at h equals 0. There's actually a hole right there. All right, but we can clearly see that the limit is 1. So, that's another one that, you could prove in analytically, but we're not going to do that. We're just going to look at the graph and say, okay, it's 1. Now, did you try this? What do you get on this? What's your first step? It's the first step on this. That derivative is going to be limit as h approaches 0. That's a 0 right there. Of e to the x plus h minus e to the x over h. How are you going to factor that? Well, let's start with, what are you going to do with e to the x plus h? How are you going to break that up? How are you going to break it up? Well, we all know that x to the a times x to the b equals x to the a plus b, right? You guys all know that. We just add the exponents, we multiply. We can run that backwards. If I have x to the a plus b, I can split it up into x to the a times x to the b. So that means that my e to the x plus h I can write as e to the x, e to the h, minus e to the x. So that was the clever part of this one, is to split this up like this. So if you thought of that, good for you. It's not as clever as some of the earlier ones that we did. So I think lots of people, even though you're first-year calculus students, could probably have figured that out. And then once you got that, since you've seen so many of these now, you can say, oh, I bet we're going to factor that e to the x out. And you're absolutely right. So this is limit as h approaches 0. And now I'm going to have e to the x times e to the h minus 1 over h. And then you see familiarly that this is just the exact limit that we just figured out. So, like having this limit is sort of your hint how to get it. If you didn't know what limit to look for, it would make this a harder problem to solve. Fortunately, you don't actually have to do these. So this is limit as h approaches 0 of e to the x times limit as h approaches 0 of e to the h minus 1 over h. The limit variable does not match the expression variable. If I evaluate by substitution, put the 0 in for the h, everywhere that there is an h, I still end up with just e to the x. This limit we just figured out is 1, so this equals e to the x. And then we discover the remarkable fact that the derivative of e to the x is just e to the x. That's actually an incredibly powerful statement that we can now sort of put some of these together that we know. So we know that the derivative of sine x is cosine x in our ever-expanding list of derivatives that you have to memorize. Derivative of cosine x is negative sine of x. Oh, it would be so nice if that was positive sine x, but it's not. And the derivative of e to the x is just e to the x. So these we looked at, this one's interesting, in terms of seasonal change. Lots of other types of changes too. The way a pendulum moves, related to this, very interesting. This one is remarkable because it really explains what exponential functions are all about. Remember that the derivative is the rate of change of the function. So you can also think of it as rate of growth, especially e to the x is always positive. So that means our rate of change is always positive, okay? So think of things that grow faster when you have more of it. Money. The more money you have, the faster it grows. So the amount is equal to the rate of change. So that's why exponential functions are good for describing financial investments. You probably A equals P e to the RT. That's a finance equation for continuously compounded interest. That e to the x says the more money I have, the faster it's going to grow. All right, population. So the more people I have, the faster the population is going to grow. Or it could be people, or it could be lemurs, or it could be frogs, or it could be trees, anything. Bacteria, viruses, all right? So number of cases in a pandemic. The more cases you have, the faster that epidemic is going to grow. We all saw that happen in real time. This is what it means, that the derivative of the function, the rate of growth, is equal to the amount that is present. Now you can modify e to the x slightly, you put some a's and b's in there, and you can find a lot of equations all involving e to the x where the rate of growth is proportional to the value of the function. And then that's the more useful thing, because generally rate of growth is not exactly equal to the value of the function. It's going to be proportional to it. So meaning the more money I have, the faster it's going to grow. The more people are infected, the faster the disease spreads, et cetera, et cetera. This also works in reverse. If you have e to the negative x, then the derivative ends up being negative e to the negative x. We'll see that later. And then you're talking about exponential decay, where the less of something I have, the slower its decay is. So again, the rate of change is proportional to the amount present. That is the defining characteristic of an exponential function, and that's what we're seeing here. The rate of change is equal to, in this case, or proportional to, in a more general equation, the value of the function. Okay, so we got some other, I think we're going to stick with these for now. And by the way, you are now already well equipped to do certain, well, let's talk about what you do need to do and what you don't need to do. So you don't need to come up with a derivation of all your derivative formulas. What you do need to do is know these formulas, so that if somebody gives you on a test or homework assignment, f of x equals x squared plus 3 e to the x minus 3 cosine x, you can say what f prime of x is. You can use your power rule, it's 2x. You can say the derivative with this multiplication, so if I have a constant multiple, I just keep it on, derivative of e to the x is e to the x. The derivative of cosine is negative sine, and that negative is going to cancel this negative, so I have plus 3 sine of x. So this is what you have to be able to do. You have to know these so you can do this. That is enough information already for you to do the Rogowski page 139. It's the same page that I posted Monday. I'll post it again. But now we're going to do the ones we skipped. Number 19, 29, 31, and 41. So those are all the ones involving e to the x. Now for some problems involving sine x and cosine x, we need one more thing. We need to talk about position, velocity, acceleration, and speed. And those are going to be actually really important calculus concepts. So that is what we'll talk about next.